Hello everyone, welcome to lecture 5 of digital signal processing. In today's class, we're going to see about oversampling A to D converters. So, what is A to D? Analog to digital. Right, so we're going to see today what is oversampling A to D converters and why are we learning this in DSP. So what the notion goes like this. It's like since the Nyquist rate got invented and we were for everybody was following the sampling rate, and the technology was advancing. So there was a need for better quality. So there was need for higher resolution, high quality, and high fidelity in terms of the reconstruction of the signals. So all this became, way upgradation. We can say like everything started getting upgraded, and that is where we are going to talk about this oversampling. So what an oversampling A to D converter means is it must have two features. The first one is it must have a sampling rate which is much larger than your Nyquist rate, and it must also use a very low resolution quantizer. So whenever we are talking about oversampling A to D converters, these 2 points must be satisfied. And why? Because these are also directly linked. Because when I say my sampling rate is very high, so I'm going to pick a lot of samples from my signals, and when I do this, when I pick a lot of samples, my samples are going to be placed close to each other. As you increase the sampling rate, the distance between the successive samples is going to reduce, or the successive samples are going to be more and more similar, or the correlation is going to get higher, right? So that is what happens when you go for a high sampling rate. Your correlation between the successive samples are going to be very high, which it is also a way of saying that your samples x of n and x of n plus or minus 1 are going to be almost equal to each other, almost the same as each other. So this is your oversampling, and when I do this oversampling, my resolution of the quantizer is going to be very small, right? So it is very understandable, because since these two samples are going to be almost same, approximately same. So when I take the difference, or when I'm planning to do quantization with these successive values, I'm going to have a very small difference, and that has to be quantized to the either upper step or the lower step, delta top or delta bottom. So the quantizer will have a very low separation between sample, or a small separation between sample, and that is your low resolution quantizer. Good. So that is your oversampling A to D. We will see more about this, the mathematics of it, the derivations of it, and what are some of the existing oversampling A to D converters designs in today's class. Good. So I'm just highlighting what is a resolution. So if some of you don't know what a resolution is, so it just a resolution is a way of saying two samples as separate points, and if you're not able to see those 2 points as separate, then you don't have a resolution there. So that is the definition of a resolution, is the closest distance where you can distinctively see these 2 points separate from one another, and that is defined as that is how your resolution is measured. Your angular resolution, your super resolution, they are measured in that manner. But for now, I will just tell that it has something to do with the separation between the points. Good. So now in oversampling, we will be seeing our quantizer is not going to be the round off quantizer that we were seeing in the sampling, but we are going to use a quantizer which is called as a differential quantizer. So a differential quantizer is different from a round off quantizer, because a differential quantizer is working with the difference between values. So the difference of values between successive samples is what is getting quantized. So it is not quantizing x of n, it is quantizing your x of n minus x of n minus 1. So its successive samples difference is getting quantized, and that is what is used in your oversampling A to D converter. Good. So what are the things we have seen so far? You have an oversampling A to D converters which is required, and it is going to follow a high sampling rate, and it is going to have a low resolution quantizer, and your normal round of quantizer is going to be replaced with a low resolution quantizer, which in this case is your differential quantizer. So this quantizer takes the difference of values x of n minus x of n minus 1, and since these differences are too small in your oversampling, the quantizer designs are also going to be much simpler, and we will see why and how in the coming slides. So let's see a little bit about the differential quantizer. So we are going to derive, we're not going to take the derivations, but we are going to just see the optimum performance. So we are using the variance of the difference between successive samples x of n minus x of n minus 1, and the variance formula is given by the expected values of d square of n. It is known and it is represented by sigma d square. So this is the formula from your statistical theory. So we are just using the formula as it is, and since my d of n is given by x of n minus x of n minus 1, I'm going to find the expected value for my d square of n and also x of n minus x of n minus 1 the whole square. So when I am going to do this, and I will end up getting the optimum variance or the optimum differential quantizer condition, which will help us in making this oversampling quantization better. So the statistics defines my variance as e of x minus mu the whole square, and mu is your mean of the distribution, and for a zero mean we just have e of x square, and here also we treat this process here as your zero mean process. So when I expand this x of n minus x of n minus 1, I'm going to get separate things like this. I'm going to expand it in the form of a minus b the whole square. So I'm going to get a square plus b square minus 2ab, and if you look here, e of x square of n, and that is going to be the variance of my signal x of n, right? And e of x square of n minus 1 is going to be the variance of my signal again, that is x of n. So that can be represented by sigma x square. So what do I have here is my e of x square of n. I have just written here that is a variance, and that is approximately equal to e of x square of n minus 1, because the successive samples and they are oversampled and the successive samples are identical to each other. Yes, so they have high similarity, or what we are going to term it as your correlation. Now, okay, I got the spelling right. I get for correlation. Now let us see what is my 2e x of n and x of n minus 1. So that is going to be a little tricky because it's taking two successive samples. So if I write that as variant of since they are approximately equal, I can write it as that also as sigma x square, but that will then just cancel out everything and you get a variance sigma d is equal to 0. So we don't want that to happen. So I'm gonna introduce an approximation here for my e of right hand side, which is e of x of n and x of n minus 1. What I'm going to introduce is this is also equal to sigma x square, but I have an autocorrelation term multiplying that. Since I am taking the expected values of two successive samples and not the same sample square, so I am going to introduce the correlation parameter r of xx. So now with this correlation, what my sigma d square simplifies to, it simplifies to 2 sigma x square minus 2x sigma x square into rxx. And if I take the 2 sigma x square outside, I'm going to get, I'm representing, this is the simplified form or the optimal quantizer sigma d, the difference variance, which is very optimal for your performance of the quantizer. And why we are using rxx of 1 is the first order, or we can say like it is a difference between successive samples. I'm taking x of n and x of n minus 1, so it is rxx 1. If I'm taking x of n and x of n minus 2, then I write it as rxx of 2. So that is the order of your correlation, or since it is between successive samples, so we are using this correlation. Now this is the optimal equation for my difference quantizer or the difference of quantizer, and now that is written as sigma d square is equal to 2 sigma x square into 1 minus rxx of 1. And now you can tell from this, so what is, before I say this is an optimal condition, in order for the optimal condition to happen, what we need to have? We need to always have our sigma d square, which is the variance of the different signal, less than sigma x square. So when this, we say that happens only when Rxx of 1 is greater than 0.5. So when that is greater than 0.5, your sigma d square is always less than sigma x square, and this is desirable. We say that this is our optimal condition. Why? Because your noise power is proportional to sigma, right, sigma x square. So which means by reducing or by increasing your sigma, right, what will happen is this sqnr improvement happens. So whenever you select sigma d square less than sigma x square, right, so you are going for a smaller variance, and that smaller variance is going to introduce a big improvement, or not, not so big, but it's definitely an improvement in your sqnr. So that is the first thing. And I would say the second thing is your sigma d square, if you're using, it's also better. So since the variation is happening at the different signal, so we can say that this reduction of variance will lead to better quantization or better approximation. Good. So, and that is happening at a lower bit rate. So this is these are two advantages, I would say, of having sigma d square less than sigma x square. First one is the low bit rate, how not important at this point. Second is your signal to noise ratio, or sqnr improvement. Good. So both of this need to be known only at the conceptual, at the basic definition, not needed for going in detail on the analysis. Okay. Now here, what I'm going to do is, this is my first, I would say this is my first optimal condition. Now I'm going for my second optimal condition. I want to do something on this, because here my Rxx1 greater than 0.5, which means between 0.5 to 1, I get my sigma d square less than sigma x square, and that is the, I say, the best condition for my oversampling quantization. But now I need to do something. I want, what if I want? So I'm again constrained with the range between 0.5 to 1. So I'm going to take the range from 0 to 1. So I want to make slight alteration, and what I'm going to do is I'm going with a difference quantizer, which is in this form. So here this a of x minus 1 is a very typical scaled one time delay circuit in DSP. So this is used in many direct form structures and cascaded structures, which we'll see on later. But for now, I can write in this form, this d of n is equal to x of n minus a, x of n minus 1. So there are two advantages for doing so. The first is the constrained limit of Rxx1, the autocorrelation from 0.5 to 1 is going to be made more broader to 0 to 1. That is the first condition that will be proven here. The second condition is this can be scaled up. So what if I want a quantizer which is not just using the difference of two successive samples, it is using a lot more samples? What if the difference is not just between two samples, and if it is using, it can happen, right? So we are looking at a very basic quantizer here, but as we advance in technology, or as we advanced in the performance, improving the performance of the quantizer, we tend to go for much upgraded designs where you may have to scale this equation for Dn. So when that happens, we may need this second optimal quantizer. So what is happening here is the same thing we are going to see exactly. Still that second last equation of sigma x square plus a square sigma x square. So what I did here is, for the best minimization, I have chosen my Rxx1 is equal to a. So when I do that, what happens is my equation becomes sigma x square into 1 minus a square, and this is a better optimal condition for my quantizer, because now here my sigma d square is less than sigma x square, if the value of a is between 0 to 1. So I have a better range here. Instead of 0.5 to 1, I'm having from 0 to 1. Good. So this is the minimization of variance or the difference quantizer for this. And now since we are using this x of n minus 1 and rx x of 1, I'm going to call this quantizer as my first order differential predictive quantizer. So what I'm predicting, right? So you may be asking what prediction we are doing. So you are predicting two things. Let us say if a is not equal to 1, you're predicting that value of a, and also you're predicting that x of n minus 1. So you don't know, right? You say that it is a delayed version of x of n, but the predictor block has to supply this x of n minus 1. So what it is going to do is it's going to take your x of n, it's going to apply the delay using the Z inverse, and then it's going to send it back to the quantizer where you can take the difference of x of n and x of n minus 1. So that is your predictor block. Good. So we will see more on the predictor block in the coming examples. Now I'll just show you how we scale this up. So I'm going to scale this a of x of n minus 1, right? That in order to scale it to order p, I'm just using this generalized expression. So for example, if p is equal to 2, then I have my difference c. Now my d of n is equal to x of n minus a1 x of n minus 1 plus a2 x2 of x of n minus 2. I call this as scaling up in order because it was order 1 to order p. But this also is another design. This is a much, these designs get, whenever you go for higher orders, you are introducing complexity. So your first order system, your LTI system, linear time invariant system, or mostly the first order system are mostly preferred. And when you go higher up, you are looking at a nonlinear system and it gets more complicated. And it's only desired in applications where, your performance is much needed, and it is very much essential to be used. Then only you go for a higher order system. So now, for a differential quantizer, your quantization error. So we are going to see all the terms that we have seen previously in normal quantization, also in oversampling here. So when you have an oversampling quantization, your difference E of n is going to be equal to D of n minus dq of n. Your d of n is the difference signal, x of n minus x of n minus 1, and your dq of n is the quantization of your different signal. Good. So now dq of n is equal to q of d of n. I can say it is a quantized version of your d of n. And now using 1 and 2, you can have a design. Right. So I can write using this 1 and 2, I can write an expression here. I'm going to write a third equation that's going to combine this 1 and 2 features. So I'm going to write it as my E of n is equal to x of n minus x hat of n minus dq of n. So I'm just combining my 1 and 2 and I'm getting my 3. So now using these three equations, I can design some quantizers. So your typical quantizer schematic or the design is going to use these three equations, and we're going to see this in this block diagram where I'm going to use mostly these three equations and some of the working of this design, and also tell you that this is going to be your quantizer for oversampling. Okay, so I'm going to I'll draw as quickly as I can. Yes. Okay, good. So now I can start labeling these blocks in this diagram. So my input is given by x of n. That's a bit small. I can go for a little more bigger version. I'll just zoom in on it a bit. Okay, good. Now this looks good. So let me start labeling these blocks. I'm having my x of n as my input, and my x of n minus 1 is coming through that because that is giving my difference of D of n, and that D of n is getting sent to the quantizer. So you see all these 1, 2, 3 equations are what basically is, keeping this schematic, or it is taking place inside this block diagram. So my dq of n is a quantized version of D of n. Then my xq of n is coming here, and this is going to be the PR block, the predictor block, because that is where I get my x hat of n. So my x hat of n can be just x of n minus 1 if I'm talking about my first order quantizer. So it doesn't have to be right. You can even write it as x of n minus 1. It doesn't matter. So my output of this quantizer, or output, it doesn't matter. Even though I'm using the difference of value, my output is always xq of n, and my xq of n is obtained in this manner. So my xq of n, if I have to write an equation for my xq of n, that is my fourth equation. So I have written 3 equations in the previous slide, and those 3 equations are available here in this block diagram. But there is also one equation which is left out from my side on that. That is the fourth equation for xq of n. My xq of n is equal to dq of n plus x hat of n. So if you see, because that is the decoder equation. For decoding, you are taking your output is xq of n, and you are taking x hat of n and adding that to dq of n. So you may ask why it is not xq of n. So why we are not taking xq of n? If somebody is looking at this very closely, there is a question that will come to your mind. So we are not taking x hat of, we are not taking the quantized x hat of n because it is a predictor block. So I have told you we are predicting. So when I'm saying predicting, we are guessing few things, right? It's like good as a guess. So when I'm guessing some, so my x hat of n is not the quantized one that is coming out of the predictor block. So when I am telling we are going to predict the value, we are allowed to use certain inputs to the predictor, so the output comes out as x hat of n, and when I am adding my x hat of n to my dq of n, I get my xq of n. Okay, so this is the fourth equation that I'm having. So I've written all the equations here. X hat of n plus dq of n is xq of n. X of n minus x hat of n is equal to d of n, and my PR is your predictor block and Q is my quantizer block. And this oversampling quantization, I call it as a differential predictive quantizer system. Good. So your oversampling A to D runs on these differential predictive quantizer system. At least that's what we are seeing here, right? We have plenty of designs. We cannot just say that this is the only design and this is the one and only for exclusive for oversampling. No, we have plenty and plenty of designs. As you open the books from various authors, you will be seeing too many designs for this quantizer. But as far as the basic DSP course for your undergraduate degree, you need to know this much at least. So next we are going to see 2 examples for this differential predictive quantizer's design. The first of which is your delta modulation, and the second is your sigma delta modulation. Now we're going to see 2 examples, one of which is delta modulation, the second one is your sigma delta modulation. So what is a delta modulation? A delta modulation is your differential predictive quantizer. It's all the things that we have seen till now, except that here we are going to use a 1-bit quantizer. So your quantizer design in your delta modulation is it works with just 1 bit. So what you can do with 1 bit, 1 bit means you're basically talking about a switch, right? It's like either 1 or 0, and that's basically what a 1-bit quantizer does. So it just checks for the difference, the difference of value d of n. It's going to take the sign of d of n, and if it is positive, it's going to give it a positive sign, and if it is negative, it's going to give it a negative sign. So it can just use 1 bit and it can quantize the value. So 1 can represent positive sign and a 0 can represent your negative sign. So that is your delta modulation. Rest of the blocks are the same, and here your PR block, your predictive block, is replaced by our typical FIR cascade, A into Z minus 1, right? A into 1 delay. So this 1-bit quantizer is our delta modulation. So it's very identical. So here what happens is you are going definitely, since it's a quantizer, it must have a step size. because quantizers produce staircase waveforms from your sinusoids. We are very aware of that. So what happens is you take the step size of delta, and then the 1-bit quantizer, what it comes up with is your sine of d of n. So if your d of n is positive, then your quantizer is gonna take plus delta, and if it is negative, it's gonna take minus delta. So your quantizer is gonna keep progressing either in the direction, either in plus delta increments or in plus minus delta increments. Here we have an example 3.1, 3.2, and my x of n minus 1 is 1 bit shifted, one delay version of x of n, and then when I'm taking the difference for x of n minus x of n minus 1, I'm getting it as 3.1, 0.2 and 0.3. And now what I'm going to do is these values, these difference values, what is the sign of these values? So it's all, yeah, so they are all positive, they are all like plus 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 plus. So which means my delta quantizer is going to just give plus delta plus delta plus delta plus delta. So it's going to give quantization values of plus delta for all these four. So my output is going to look like 1-bit quantizer is going to be all plus delta, and then it will go on to the decoder, and we will extract, we'll get this back at the decoder side, and that is why we have the predictive block which will give you the first value. So we don't need that many details, we're not going to see, because it is a topic for digital communication. So encoding and decoding mostly comes in your communication. In signal processing, we are only interested in the things that work with signal. So for that we have seen enough. So now we will see the illustrations for the delta modulation. So you have a sinusoidal signal, and when you do your 1-bit quantization on it, you are going to get a staircase waveform. So every time it is a 1-bit quantizer, because it's always incrementing in plus delta, and for negative slope it's gonna come to minus delta. Positive slope you will have plus delta, negative slope you will have minus delta. So the staircase waveform, and when you encode it, you are basically sending this staircase waveform as a flat waveform. So you are removing that slope and putting some encoding coding theorems on it, and just organizing it in this, or just representing it in this flat line without the slope. And at decoding you are doing the exact reverse. So when I say encoding, it's not just like no slope, it's like it is also having certain other features, like we have variable length coding, run length coding. So there are some algorithms that goes into this encoding, but it is basically, if you are taking a very simple encoding without any of these theories on it, or any of these algorithms, you can just say that you have taken your staircase waveform, you have removed the slope, and you have just packing it as your encoded pulse waveform. So this is your schematic of a delta modulation. And now another important thing here is the low pass filter. So just look at this low pass filter. It's a very good question, and many of them ask, how do you convert your staircase waveform into a sinusoidal signal? A staircase waveform can be converted into a sinusoidal signal using a low pass filter, because low pass filter is gonna smoothen. So low pass filter is also called as a smoothening filter, and your high pass filter is a sharpening filter. So when you smoothen a staircase waveform, you are getting a sinusoidal signal, which is shown here. And how do you generate a staircase waveform from sampling, or generate a staircase waveform from your sinusoidal signal? You just do a 1-bit quantization, you just do a delta on it, you just do a delta quantization, and you get your staircase waveform. So very, very important. Sinusoids to staircase using delta, and staircase to sinusoids using low pass filter. Next, we are going to see what are some of the drawbacks. So these are all the advantages of using a 1-bit quantizer. So it's simplicity in design, right? It's very simple to implement. It's just too easy, right? You can see, the design, if it's too easy, and to implement it, it doesn't require much sophistication in terms of hardware and other equipment. But what is the drawback? Does it have any disadvantage? Yes, there are two big drawbacks for your delta modulation, one of which is called as the slope overload distortion, and another one is known as your granular noise. So a slope overload distortion happens when your slope overshoots, or when you have a very steep slope, and your granular distortion happens when you have a zero slope. So these are like vice versa cases, right? One happens when your slope is to slip almost close to vertical, and the other happens when your slope is almost close to zero or a horizontal. So that is your slope overload and your granular noise. Now, the when do these happens? So it's very obvious, right? Whenever you have a steep slope, it will happen. That is obvious. And this is also the reason. Oh, very good, very good. I can tell you about why we don't use a square wave here, right? We don't use a square wave or an exponential signal because your square wave is going to have a very steep slope. It's almost like a vertical slope, 90-degree, and then your exponential signals have a long tail which will produce granular noise. So the best signal to avoid slope overload and granular noise is your sinusoids, because they have a moderately good slope and they don't have too much of an exponential tail like an exponential signal. So a sinusoid signal is the best signal we can use in for your delta modulation, and it will have the minimal slope overload and granular noise. So now we will see how to overcome these two, slope overload and granular noise. So from this figure, you can see that your steep slope, you have a slope overload problem when your step size is smaller, because whenever your step size is smaller, your quantizer cannot capture the steep slope, right? It falls behind, it falls short of the steep slope, and that is your this one. And now what happens is, when you have a granular noise, for the granular noise it is the opposite. So the conditions that I am using here is the d by dt of x of t, which is the slope of my sinusoid, is less than step size delta, right, by ts. So, or in other case, when the step size is small, like in this case, you have a slope overload distortion. And when the step size, to overcome the slope overload distortion, you just make the step size bigger. So when your step size is increased, your slope overload distortion reduces or it vanishes completely. But now this is also a vice versa case. What happens is, when your step size is large, your granular noise is large. As you can see, granular noise happens on the flat region of your signal, and at flat region of the signal you don't have much variation, so you need to have a step size as small as possible. So which means if you're having a signal which is having both steep slope and a flat area, so which means it's going to have both slope overload distortion and granular noise. And if you want to overcome the slope overload completely, then it will compromise on the granular noise. So granular noise will shoot up. So there is always a trade-off. So it's better to choose a value for step size that will reduce a bit of slope overload and also your granular noise. If you are having a signal which is having only one of these distortions, then you don't have a problem. You can go for any of this. You can either increase the step size to overcome the slope overload, and you can decrease the step size to overcome granular noise. Understood? So increasing step size reduces slope overload but increases granular noise, and vice versa. Good. So I hope it is not confusing. The figure should make this clear. I felt a lot of increase decrease I have told in that slide. Just hope seeing the slide you don't get confused with my analogy of things. So next is your sigma delta modulation. So so we have seen delta modulation. Your sigma delta modulation is something that is you can call it as a much, what you call as like a modulation that emphasizes on the low pass filters. So now I have told you a very good this thing is, you take a sinusoid signal, you do the 1-bit modulation or the 1-bit quantization, you get the staircase waveform. Same way, you take the staircase waveform and you do the LPF or the low pass filter, you get the you get the smoothened signal, or you get the sinusoid back. So you see, no, that low pass filter is having a role in this delta modulation, and now your low pass filter is nothing, a filter which works with the low frequencies. So now what we do in our sigma delta modulation is we are going to bring in an integrator, which is our sigma. So the sigma stands for the integrator because in discrete time your integrator is a sigma, right? So that is the integral in continuous time is equal to sigma in discrete time. So that is your sigma delta modulation, all at very broad level. We are not going in depth of sigma delta modulation. So what sigma delta modulation is doing is it emphasizes on low frequencies. So how does it emphasize on low frequencies? By using an integrator which is also acting as a low pass filter. So when I integrate a sinusoid, I'm getting integral of sine omega t is 1 by omega sine omega t, and that is 1 by f, which means for small f's my 1 by f becomes a big value or a large value, and that means my integrator is emphasizing, or integrator is better for low frequencies, you can say. And when you do the differentiation, you are doing the opposite. So differentiation is going to give f into sine omega of t, so your differentiator works well for high frequencies. Good. So that is the reason why your integrator is used as a low pass filter and your differentiator is used as a high pass filter. So the integrator that we use in sigma delta is not a mathematical integrator, right? We are going for, typically we use an op-amp design, but we are not no concerned with that. We just need to know the why, what is sigma delta modulation and why it is used for our oversampling. Because it is used for our oversampling because it is because of the low pass filters. We are taking in our differential, in our quantization, you are having your staircase waveform, and for staircase waveform to become a sinusoid you are using an LPF. So now the question is, what if I used the same LPF at encoder and decoder? Because you are using an LPF at the decoder but you are not using a low pass filter at the encoder. Your encoder was deprived of an low pass filter or an integrator in the delta modulation. In sigma delta modulation you are using a LPF or the integrator, which is the low pass filter, in the encoder and also at the decoder. So which means you can tune your encoder LPF and the decoder LPF in such a way that you get the best reconstruction output. So sigma delta modulation is an improved version of your delta modulation because of the low pass filter syncing with your integrator at the encoding decoding process. Understood? So this is your sigma delta modulation. I think today's class covers most of it. So whatever we have seen are important. We have seen everything related to your oversampling, A to D converters, and when I talk oversampling, you have a high sampling rate, a low resolution quantizer, and what is the design of the quantizer? A high sampling rate can be achieved just by increasing your f of s or the Nyquist rate way above 2f max. So we are just increasing the sampling rate, which means your samples are going to be closely placed, and for that you need to adjust your quantizer, and that is the designs we have seen today. We have seen your first order predictor differential quantizer. We have seen few examples for those quantizers, which are your delta modulation and your sigma delta modulation. Sigma delta modulation is much efficient because it uses an LPF on the encoder side and also on the decoder side, which can be synced together to get best reconstruction results. Thank you for listening. I'll be back with more lectures.